Hello, so in this video we're going to be talking about the variety of space telescopes that are used in astronomy. And many of us have used telescopes occasionally as a child or maybe even as adults. And usually we use visible light telescopes. And these telescopes mainly use mirrors to focus, mirrors or lenses to focus light and essentially magnify the image and brightness of the image so that we can see more detailed features. For example, when we look at the moon, we can't really see the craters of the moon from our own eyes. But when we use a telescope, the moon is zoomed up and it's also brightened up so we can see more clearly. So visible light telescopes are mostly for us amateurs, but professional astronomers use a much larger variety because there's a lot of information that we can tell from the different types of telescopes that we use. One of the reasons we do this is that electromagnetic waves, which is basically what a telescope is, they travel through space differently and they form in different environments. And so being able to detect all of these different wavelengths at these different environments really helps us understand the system we're observing at a more fundamental level. The first type of telescope I'm going to talk about are radio telescopes. These telescopes, they're not really useful to look at with your own eyes. You need a computer to process the image, but they essentially tell us about really large scale structures. For example, radio galaxies are a common one. Radio waves are really useful in mapping out, the large scale structure of the galaxy's lobes and jets of gas out of their supermassive black holes. Um, Radio telescopes are also useful because there are interesting phenomena in the universe known as very fast radio bursts, and we don't really entirely understand them, but they are really crucial. They were actually really crucial in helping us really map out the matter of the universe and actually confirming that the amount of ordinary matter predicted in the universe is what it should be. So those are the applications for radio waves. Next, we're going to move on to microwaves. Microwave telescopes are, but they do observe shorter wavelengths, so it's not really a radio telescope. And the main thing they're responsible for observing is the cosmic microwave background radiation. This radiation originated from the really primitive origins of the universe, around 300 to 400,000 years after the universe had formed. So the initial microwave telescopes that were launched, such as COBE and WMAP, these orbiting space observatories were able to essentially map out the sky's microwave radiation and, in essence, basically find out where the matter of the universe is located, which is really cool to know. And since we're looking back so far into time, we're essentially looking at the beginnings of the universe, which is a really cool thing to be able to do. The next one we're going to be talking about is infrared telescopes, and most famous example of infrared telescopes is the Spitzer telescope, which is unfortunately retired now, but it was really useful in observing really young stellar nebula mostly, and any type of radiation that is cloaked with a gas or dust in visible light. The reason why is because infrared radiation can go through a lot of this gas and dust unimpeded, and so you can really see things that you would otherwise not see from the naked eye. One common example uh, is the Pistol Star. The Pistol Star is the most luminous star in the Milky Way galaxy, but we have not actually ever seen it in terms of visible light because it is surrounded by its own nebula, and so you can't really see it. So essentially how we've seen it is through infrared light, where the infrared light, the heat of the star can go through the gas and dust, and you can actually see the star that way. Another famous example is the Cone Nebula, which if you see normally you only see a few really large luminous stars, but if you look through infrared light, you can see there's dozens of really small stars that are forming, and that's really only possible to view from infrared light. The next type of telescopes is obviously visible light, and visible light telescopes are useful because they give an accurate impression of what things look like with the human eye. And most the most famous visible light telescope is the Hubble Space Telescope, and which has been giving us great pictures of things really far, beyond our imaginations for the past 20 years, which is really amazing. One reason why we only see invisible light, just a quick fact, is because the atmosphere really is only transparent to visible light and radio waves, which is why we also have radio telescopes here on Earth, but not really any other kind of telescopes besides visible and radio wave telescopes. And since visible light has much more energy and has a much shorter wavelength than radio waves, it's more practical to use visible light to see everyday objects, which is why life on Earth mainly involved to use visible light, and in some cases, animals can see ultraviolet light as well, which is really interesting. Ultraviolet telescopes usually they're not really some. There are some specialized ultraviolet telescopes, but ultraviolet light mainly helps to observe things that are slightly harder than usual than like your normal visible light category of objects. For example, our sun is the brightest in yellow light, and so observing invisible light will give it its maximum brightness. But there are other stars and other regions where there's a lot of high mass stars, and those mostly emit ultraviolet light. So ultraviolet telescopes are really useful for detecting those types of objects, those more luminous objects that are not really powered by stellar remnants such as supernova, white dwarfs, neutron stars, and black holes. So after the UV light comes X-rays, and the most famous observatory for that is the Chandra X-ray Observatory. And X-rays are really useful because they're really commonly found around really high energy systems, the most common being around black holes. So whenever anything falls into a black hole, usually it's torn apart and it forms an accretion disk. This accretion just gets really hot, up to a few million degrees Celsius, and at that high temperatures emits a lot of X-rays. So usually X-rays of this type are really luminous, and most of the X-ray sources in the sky are from these types of systems. Neutron stars can also form accretion disks and can also form really high energy X-rays. Sometimes they also form pulsars, which can also be detected in radio waves. Neutron stars produce a really large variety of wavelengths. Finally, we move on to gamma rays. And so gamma rays are the most energetic type of electromagnetic wave, and so however, they cannot really penetrate the atmosphere because the atmosphere shields us from high energy radiation. So we really need go out into space to actually see gamma rays, which is why we have gamma ray observatories. But gamma rays, since they're also high energy, they can't really be focused as much because they will go right through a mirror, like a mirror if you try to focus it too much. And so they really just they give you a general idea of where things occur. Really high energy events such as gamma ray bursts. And so gamma rays really tell us about how unique or how uniform the universe is. Um, for example, gamma ray bursts, they've been found to occur at pretty much random locations in the night sky, which means that they're equally distributed throughout the universe. And they're also really high energy events, which is also really interesting because we really don't know much about these stellar processes that happen towards the end of a star's life cycle. Um, so gamma rays can tell us like the locations of gravitational wave mergers. They can tell us about black holes merging with each other. They produce a big explosion, and that could be a source of gamma rays. They could also be telling us about two neutron stars colliding with each other. When they collide together, they also release a huge amount of gamma rays. Combining this with gravitational wave data, you can actually pinpoint where these neutron star mergers are happening. Neutron star and black hole mergers are happening. So yeah, that's basically all I have to share about space telescopes. If you have any questions or would like to suggest to me any topic, any video topic that you would like for me to make sure you comment below. And if you're interested into me making more random science content, feel free to subscribe as well. Thank you. I hope you have a good day.